Hello and welcome back. We're going to look at the half-life of a reaction. We often give it the symbol T sub 1/2, and this is the time it takes for half the reactants to be used up. One of the really neat things about the half-life is it actually depends on the type of reaction. It depends on the order of the reaction. So that is the power that the reactant experiences in the rate law. And if you've got a zero order reaction, okay, we can go ahead and we can calculate the half-life as follows. So what we're going to go ahead and do is we're going to say at time equals 0, the concentration at the start of the experiment, right, is just going to be the concentration at the start of the experiment. But at a time given by the half-life, the concentration at that time is going to be 1/2 of the original concentration. All right, so this is a zero order reaction, and we can go ahead and we can write down the equation for a zero order reaction. So in the last video, we saw that the concentration at time t is equal to minus k times t plus the original concentration, and so we can substitute stuff in here now. So we can say, well, the concentration at time t, we're letting that be half of the original concentration. The time t, right, we're going to call the half-life. And so now we have an expression here, so we can just kind of move it up here. So we've got 1/2 of a sub 0 is equal to minus k times by the half-life plus the original concentration. So we want to focus in on this. So let's see, how can we do it? So we can subtract a sub 0 from both sides. So then we've got minus 1/2 a sub 0 on the left is equal to minus k times by t sub half, right? So we basically subtracted that from the right and from the left. And now we want to solve for that. So we just divide by minus k. So then we get t sub 1/2 is equal to minus 1/2 a0 over minus k. And I suppose we can write that as a sub 0 over 2k. So that's an expression for the half-life. And if we try and interpret this equation, if we want to kind of figure out what this equation is telling us, it's telling us that the lower the original concentration is, the shorter the half-life. So the half-life is changing throughout the reaction, but it gets faster and faster for half of it to be used up. Let's pull up another slide and see why. So if we look at a zero order reaction, essentially the concentration versus time plot is a straight line. And it looks essentially something like that. And the half-life is the amount of time it takes for half of it to be used up. So for instance, there's my original concentration, and there's half of it. And if I want to go ahead and see how long it takes for my first half-life, all right, there we go. Now my second half-life, so I am starting here and here, right, and I'm going down to here. All right, so how long does it take? Well, it's taken a lot less time now. And if I look at my third half-life, so I'm starting here and I'm going down to half that value. So if I draw that in green, then it is taking less and less and less time. So each half-life, so the original half-life is right here. The second half-life is here. The third half-life is here, right? We can see the time it's taken for half the reaction to be used up is getting smaller and smaller and smaller. And that's actually another way we can recognize a zero-order reaction. So if we've got a zero-order reaction and we know the amount of time it takes for half the stuff to be used up, if that time keeps getting shorter and shorter, then that's a hint it actually is a zero-order reaction. And let's look in another video at what happens if you get a first-order reaction, because we'll see the behavior for a first-order reaction is totally different than a zero-order reaction.